Hello everybody, welcome into another lesson. So today we are going to talk about graphing basic rational functions in the form of ones like f of x equals 1 over x. So for today's lesson we will have a constant divided by a linear x term. So you'll have a constant in the numerator and then you'll have a linear x term, or x equation, I should say, in the denominator. So, of course, we have f of x equals 1 over x. So, what we have to consider is one thing. When you look at 1 divided by x, what is true of a fraction in general? You cannot have a denominator value equal to 0, right? First thing you always want to do is take your denominator, set it equal to 0. In this case, your denominator is x, so take that x equal to 0. So what is x equals 0? That would make this undefined, right? So that means when x equals 0, that is your vertical asymptote. So you actually have a vertical asymptote at x equals 0. Alright? Or whenever that denominator equals 0, this will be when you'll have a vertical asymptote. So basically, for rational functions, and when we graph it, I'll explain more, anytime your denominator can be equal to 0, that's where you have a vertical asymptote. And in some of these, you'll have more than one vertical asymptote if you have a quadratic expression in the denominator, which we're not going to do today, but we will in future lessons. Now, you just have a constant over a linear x expression, right? You also have a default horizontal asymptote at y equals 0. So every time you have a constant divided by a linear x expression, you have y equals 0 as a horizontal asymptote. So you have x equals 0, which is the entire y-axis, as your vertical asymptote. Then you have y equals 0, which is the entire x-axis, as your horizontal asymptote. So now let's get to graphing this. So let's pick x equals positive 1. Well, you would get 1 divided by 1, right? Which would just give you 1. So when x is 1, y is 1. Now what about when x is 2? You would get a y value of 1/2, right? So that would put you about right there. Then when x is 3, you would get 1/3. And do you notice the pattern that the higher up you go in your x values, the closer to a y value of 0 you're getting? You can't actually hit 0, but you're going to get really close. That's why y equals 0 is a horizontal asymptote. Now, let's say x equals 1/2. Well, what is 1 divided by 1/2? That would be 2, right? So when x is 1/2, you have a y value of 2. And then when, let's say, x is 1/3, you would have a y value of 3, right? So notice, the smaller the x value you have, the higher up in y you're getting, and it's getting infinitely close to x equals 0, but it can't actually reach it. So that's where x is your vertical asymptote. So let's go ahead and graph this branch of the function. Alright, so there's that branch. Now we have to consider also when x is -1. So if you put -1 in for x, you would get a y value of -1. And then when you have x equals -2, you would get a value of -1/2 for y. And then let's put in -3 for x. You would end up getting a y value of -1/3. Notice again, it's getting infinitely close to a y value of 0, but it can't quite reach it. Now, what about, let's say x equals negative 1/2. 1 divided by negative 1/2 will give you a y value of negative 2. And then let's take x equals negative 1/3. 1 divided by negative 1/3 is negative 3. So notice, again, you're getting infinitely close to that x value of 0, but you can't quite reach it. So now let's go ahead and connect this side here. And this is what you're going to have. You have two branches of this rational function, to the right of x equals 0 and to the left of x equals 0. But x never actually equals 0 because that would give you an undefined value. So when you have a shape like this with two curves such as this is called a hyperbola. So you get what is called a hyperbola. That's more of a bit of trivia for you right now. But in the next section of the course, we're going to get into conic sections, which hyperbola is one of the topics we're going to talk about, along with circles, parabolas, and ellipses. But that's a little while from now. But anyway, let's go ahead here and continue with this. So let's show a transformation. What if this time I did f of x equals negative 1 divided by x? So f of x equals negative 1 divided by x. So this is definitely going to be a reflection, right? Because you have a negative coefficient. Well, if you set the denominator equal to 0, x equals 0, you still have a vertical asymptote. That much is true. A vertical asymptote of x equals 0. And then you have a constant divided by a linear x expression. You get a horizontal asymptote also of y equals 0. That hasn't changed. But what is going to change is the placement of the hyperbola. So let's do x equals positive 1. That would give you negative 1 for y, right? What about when x equals 2? That would give you a value of negative 1/2, right? And then what about when x equals 3? That would give you negative 1/3. And then what about when x equals 1/2? You would get negative 2. And then when x equals 1/3, you would get negative 3. So notice with this branch of the graph, we've reflected it in the x-axis. Because normally it goes like this if it's positive 1 over x. Well, we have just reflected this in the x-axis, and the same is going to be true for the other side. So what about when x equals negative 1? You would actually get a y value of positive 1. Now what about when x equals negative 2? You would get a y value of 1/2. What about when x equals negative 3? You would get a y value of positive 1/3. Okay. Now what about when x equals negative 1/2? You would get a y value of positive 2. And then if x equals negative 1/3, you would get a positive y value of 3. So let's go ahead and draw this branch out. So we have also taken the original graph and reflected it in the x-axis from where it originally was. You could also argue it's reflected in the y because it's tilted around. You could also argue that. So really this is a reflection in both the x and y-axis when you have a negative constant on a rational function, when you have a constant in the numerator and a linear x expression in the denominator. Okay. So there is that. Now, let's do some other functions here, like that are rational. This time, let's say we have f of x equals 4 divided by x. So f of x equals 4 divided by x. Well, find your vertical asymptote first. That's going to be when x equals 0. So x equals 0 is your vertical asymptote. Now, your horizontal asymptote, since you have a constant in the numerator and a linear x expression in the denominator, you have a default horizontal asymptote of y equals 0. So that hasn't changed, but you have the constant of positive 4. This is a stretching factor of 4. So let's go ahead and put this together. What about when x is 1? Well, 4 divided by 1 is 4, so you'll get a y value all the way up to 4. Okay, what about when x is 2? So 4 divided by 2 is what? That's going to be 2. Then 4 divided by 3, that's 1 1/3, so that'd be right about there. 4 divided by 4 is 1. 4 divided by 5 is 4/5, that'd be right about there. 4 divided by 6 is 2/3. Then you have 4/7. 4/8 would be about 1/2, and then 4/9. It just keeps getting smaller and smaller. Now, what about 4 divided by 1/2? That actually puts you all the way at x equals 8, and then you see it just keeps going up and up, but it's stretched. It looks a little bit different because it's stretched. All right. Now, what about the other side? So when x equals -1, you would get, of course, -4 for your y value. Now, what about when x equals -2? That would give you a y value of -2. What about when x equals -3? That would give you -1 1/3. X equals -4, that would give you -1. X equals -5, that would give you -4/5. X equals -4/6, that'd be -2/3. And you see the pattern, what it's just going to keep on doing here. It's going to keep doing the same thing. The only difference is you have a stretching factor of 4. But it looks sort of identical to 1 over x, except you have that stretching factor of 4. So that's general rational functions. Now let's throw in some other types of shifts into the mix. I think we get the general concept of rational functions. Let me see something. All right. So, what if this time I'm going to throw something different in? What if f of x equals 3 divided by x minus 3? All right, so this has just changed a little bit. We have f of x equals 3 divided by x minus 3. What is happening here? This is going to be, so if it's shifting in the x direction, if it's a change on x in the denominator, if you're doing plus or minus, that's a horizontal change. It's shifting to the left or right that many units. The general form for a rational function is f of x equals a all over x minus h plus k. That a, of course, is the constant. That x, and then your minus h, that's a shift either left or right. And then pretty soon we'll get to plus k, which is a shift up or down, vertically. So that's the general form for a rational function, at least where you have a linear expression in the denominator. Now, what you have to do take your denominator, set it equal to 0. So take x minus 3, set that equal to 0. Well, you would get x equals 3, right? So x equals 3 is your vertical asymptote. So you actually have a vertical asymptote at x equals 3. So why don't we plot that here? Why don't we draw our vertical asymptote at x equals 3? Just to delineate where we're going to be, because everything has shifted to the right 3 units. Alright, so there's our vertical asymptote of x equals 3 in red. Now, what about for a horizontal asymptote? Well, still, you have a constant over a linear x expression. You have a default horizontal asymptote of y equals 0. So that hasn't changed. Now, since everything shifted to the right 3, let's start when x equals 4. So what is 4 minus 3? That's 1. 3 over 1 is 3. So at 4, you'll have a y value of 3. All right, so now what about when x equals 5? Well, what's 5 minus 3? That's 2. You would get 3 halves when x equals 5. So that'd be 1.5 when x equals 5. And then what about when x equals 6? Well, 6 minus 3 is 3. 3 divided by 3 is 1, so you'll be at 1. All right, 7 minus 3. Well, when x is 7, 7 minus 3 is 4. Then you get 3/4 for your y value. And then you see what it's doing. It's still getting closer and closer to that horizontal asymptote of y equals 0, but it's going to go up and get closer and closer to x equals 3, but not quite be able to do it. Because if you put in 3 for x, you would have 3 divided by 0, which would be undefined. Alright, so what about when x equals 2? Let's do positive 2 for x. So 2 minus 3 is what? Negative 1, okay. 3 divided by negative 1 is negative 3. So at 2, you're all the way down to negative 3. Alright. Now, what about when x equals negative 1? So, when x equals 1. 1 minus 3 is negative 2. You would get negative 3 halves, so that would be negative 1.5. What about when x is 0? You would get 3 divided by negative 3, which would be negative 1. So yes, we can in this case cross the y-axis because that's not our vertical asymptote. Our vertical asymptote is x equals 3. Now what about when x actually equals negative 1? Negative 1 minus 3 is negative 4. You would get a y value of negative 3/4. And then when x equals negative 2 minus 3 is negative 5. You would get negative 3/5. And you see it's just getting closer and closer to that y value of 0 up here. You see it still can't quite reach the asymptotes, but everything has shifted to the right 3 units. Alright, now, I think that much is pretty easy. But let's throw in another curveball here. Let's throw in another. What if I did 1 divided by x minus 7 plus 3? So f of x equals 1 divided by x minus 7 plus 3. So what's going on here? Well, you notice that minus 7, that means that everything's going to shift to the right 7 units. And then that whole fraction plus 3 means everything's shifting upward 3 units. So set your x minus 7 equal to 0. If you do that, of course you're going to get an x value of 7. X equals 7, that would be your vertical asymptote. So that is your vertical asymptote. So why don't we go ahead here and draw our vertical asymptote at the point x equals 7. All right. Now, what about a horizontal asymptote? So we know everything shifted to the right 7 units, right? What about a horizontal asymptote? Well, what's true here is you have a constant divided by a linear x expression, so by default that would be 0. However, that plus 3 outside of the fraction means you shift everything upward 3 units. So in actuality, y equals 3 will be your horizontal asymptote. So that also shifts your asymptote upward. So y equals 3 is your horizontal asymptote. Let's go ahead and draw that in. So this looks very interesting now, doesn't it? Shifted vertical and horizontal asymptotes. Okay, let's start graphing. So x can't be 7, that would be undefined, right? You get a 0 in the denominator, but what about when x is 8? 8 minus 7 is 1, 1 divided by 1 is 1, plus 3 is 4. So when x is 8, you'll get a y value of 4. What about 9? So 9 minus 7 is 2. 1 divided by 2 is 1/2 plus 3. That would give you 3.5. And let's go to 10. So what is 10 minus 7? That's 3. 1 divided by 3 is 1/3 plus 3 is 3 1/3. So notice, you're getting closer and closer to that y value of 3, but you can't quite hit it. And it's going to get closer and closer to that x value of 7 on the left and keep increasing infinitely, but it can't quite make it. All right, let's go to the left of x equals 7. What about when x equals 6? So 6 minus 7 is what? Negative 1. 1 over negative 1 is negative 1 plus 3 is 2. So at negative 6, you'll get a y value of, at positive 6, you'll get a y value of 2. Now what about when x is 5? 5 minus 7 is negative 1/2. No, sorry, 5 minus 7 is negative 2. 1 divided by that's negative 1/2 plus 3. You would end up getting 2.5. All right, now what about when x equals 4? So 4 minus 7 is what? That's negative 3. 1 divided by negative 3 is negative 1/3. Plus 3, that's 2 2/3. So you see you're getting closer to that y value of 3 on the left-hand side, but you can't quite get your act together and reach it. And then the same thing happens over here. So you have shifted everything to the right 7 units and up 3 units. All right. How about, let's see, f of x equals negative 4 over x minus 5, all that minus 8. So f of x equals negative 4 divided by x minus 5, all that minus 8. So what's really going on here? That x minus 5 in the denominator means everything's shifting to the right 5 units, and then that minus 8 to the side of the fraction means we're shifting everything downward 8 units. So, what does this mean for our asymptotes? Well, the x minus 5, you set that equal to 0. What are you going to get for x? Of course, you'll get x equals 5. That would be your vertical asymptote. So let's go ahead and plot our vertical asymptote here in red marker. So 1, 2, 3, 4, 5 right there. All right, now what about the horizontal asymptote? Well, again, a constant divided by a linear x expression gives you a zero default horizontal asymptote at y equals 0, but we're shifting everything downward 8 units. So really, it's going to be y equals -8 will be your horizontal asymptote. So y equals -8 is actually your horizontal asymptote. Okay, so let's fill that in too, huh? Let's come all the way over here. All right, so we've plotted both asymptotes now. And notice we have a negative constant in the numerator, so we're actually going to have a reflection of the normal rational function in the x and y axis also. So let's start out like normal. Let's go to the right of x equals 5. Let's start with x equals 6. So what is 6 minus 5? That's 1. Negative 4 over 1 is what? Negative 4 minus 8 is negative 12. Well, that's going to put you all the way down here somewhere off the board. Let's just do down here. What about when x equals 7? What is 7 minus 5? That's 2. So negative 4 minus 5, sorry, negative 4 over 2 is negative 2 minus 8 is negative 10. So at 7 you get negative 10. Now what about when x is 8? 8 minus 5 is 3. Negative 4 over 3, that's negative 1 1/3. Minus 8 is negative 9 1/3. And then when x is 9, so 9 minus 5 is 4. Negative 4 over 4 is negative 1. Minus 8 is negative 9. And then what about when x is 10? So 10 minus 5 is 5. Negative 4/5 minus 8 is negative 8 4/5. So you see what it's doing here, and it's going to be hard to continue. But somewhere all the way down past the board, it would get close to that horizontal, that vertical asymptote of x equals 5. It's just off the board. It's a little bit hard. Now let's go to the left. What about when x equals 4? 4 minus 5 is negative 1. Negative 4 divided by negative 1 is positive 4. So positive 4 minus 8 is negative 4. So negative 4. What about when x is 3? 3 minus 5 is what? That's negative 2. Negative 4 divided by negative 2 is going to be 2 minus 8 is negative 6. And then you're going to have, what about when you have 2? 2 minus 5 is negative 3, so negative 4/3 is 1 1/3 minus 8 is negative, that'd be negative 6 2/3, so you see eventually it's going to start getting closer to that line of, it's going to take a while, but we get close to that line of the 7 of, I'm sorry, x equals 5 and y equals negative 8. And it does something similar reflected down here to the right side. I just couldn't draw all the way. But everything shifted to the right 5 units, down 8 units, and reflected in both axes. So that one was a good one. All right. Why don't we do one more? So let's do 4 divided by 3x minus 6 plus 5. So we have 4 divided by 3x minus 6, all that plus 5. What are we going to do? Again, start out setting your denominator equal to 0. So 3x minus 6 equals 0, right? That's going to mean 3x equals 6. That means that x equals 2. So you're going to have a vertical asymptote at x equals 2. So why don't we go ahead and plot our vertical asymptote at x equals 2. So yes, the denominator's still linear, but the coefficient's not 1. But it's the same process. Just set your denominator equal to 0, and that value for x that you get will be your vertical asymptote. Okay. Now, what about for a horizontal asymptote? Well, a constant divided by a linear x expression would give you a default 0, y equals 0 horizontal asymptote, but everything is shifted upward 5 units. So you have a horizontal asymptote of y equals 5. So why don't we plot y equals 5 as the horizontal asymptote? Right there. There we go. Perfect. All right. So this is where it gets fun. We still need to go to the right of x equals 2 to start. So let's put in f of 3. What do you get? F of 3, so that's going to give you 4 over 9 minus 6 plus 5. Well, that equals 4/3 plus 5, which is 1 1/3 plus 5, so you would end up getting 6 1/3. So when x is 3, you would end up getting a y value of 6 1/3. All right, now, what about, basically you're just going to have to plug in a few values here. So what about when we take f of 4, when x is 4? So this would be the same as 4 over 12 minus 6 plus 5, which equals 4/6 plus 5. Well, what's 4/6? That's 2/3. So that's going to give you 5 2/3. So when x is 4, you'll end up getting 5 2/3. And for good measure, why don't we do f of 5? Just for one more. So f of 5, that's going to equal 4 over 15 minus 6 plus 5, which is equal to 4/9 plus 5, which is simply 5 4/9. A little less than 5 1/2. So about right there. And you see the pattern that this graph is starting to take, closing in on the horizontal asymptote of y equals 5, and then to the left, closing in on the vertical asymptote of x equals 2. All right, now what do we got to do? We need to go to the left of x equals 2, so let's pick x equals 1. So f of 1, that of course equals 4 all over 3 minus 6 plus 5. What does that equal? That equals negative 4/3 plus 5, which would have to equal 11/3, which we know is 3 2/3. So you'd end up when x is 1, you get 3 2/3 for your y value. All right, now why don't we pick x is 0? So let's do x is 0. So that's going to be 4 over negative 6 plus 5, which would equal negative 2/3 plus 5, which would end up equaling 4 1/3. So when x is 0, you end up getting 4 1/3, which is about right there. And then, of course, let's do f of negative 1. So negative 1, f of negative 1, so that's going to be 4 over negative 3 minus 6 plus 5. Well, that would equal negative 4/9 plus 5, which would end up equaling 4 5/9. So a little over 4 1/2. So you see the shape it's taking. To the left, it's getting closer and closer to that y value of 5, but not quite able to reach it. Then to the right, it's getting closer and closer to that x value of 2, but not quite able to reach it. So there would be the graph of this rational function. So really, that's it for basic rational functions. The next lesson, we're going to do this in 3 parts. The next lesson will be about graphing rational functions where the degree of the numerator is less than the degree of the denominator. And then after that, we'll do where the degree of the numerator is equal to the degree of the denominator. Then after that, we'll do when the degree of the numerator is greater than the degree of the denominator. So we'll have 3 lessons on graphing these. So I hope everyone has a great night. Take care.